In this video, we're going to talk about acid dissociation problems, and we're going to use the ice table method to solve an example. So the acid dissociation constant, which is usually written as Ka, is a measure of the strength of an acid in solution. It is the equilibrium constant for an acid dissociation reaction. So, say we have a reaction where some acid, HA, goes to equilibrium with its counterions, H plus A minus. Our Ka is going to equal the concentration of our products over the concentration of our reactants, just like a normal equilibrium constant. So now let's do an example with an ice table. So we have 5 molar HNO2 is going to dissociate into H plus and NO2 minus according to its acid dissociation constant, Ka, which equals 4.0 times 10 to the negative fourth. And we're going to determine the equilibrium concentration of HNO2, H plus, and NO2 minus. So the first thing let's do is let's set up our reaction. So our reaction for this is we're going to have HNO2, and it's going to come to equilibrium with its dissociated products, which is going to be our H plus and our NO2 minus. And now we're going to write out our ice table. So ice table is actually an acronym. The ICE means initial, change, and equilibrium. So our first row is our initial values. So what we do is we put in our initial values for the molarity of our species that we're looking at. So we're just going to draw our table right under our equation here so that it's really easy to see which column goes to which chemical. So the initial concentration of HNO2 we said was 5 molar. I'm just going to put a big M here for molar, just to remind us that we only put molarities into the ice table. So we're going to write a note about that. Okay, so our initial concentration of H plus and NO2 minus, we're going to say is 0. Now, if we had a very weak acid, we might want to just put in the amount of H plus that we get just from water disassociating. But in this problem, with our Ka being this large, it's only times 10 to the negative fourth, that won't really factor in. So next we're going to look at our change, and our change is going to tell us what's going to happen. So let's just write down our steps we've done so far so we can make sure we keep up with this. So the first step we did is put in our initial concentrations. Now we said our second step is we're going to use stoichiometry coefficients to determine what change would occur if X amount of the acid dissociated. Okay, so we're going to say X amount of the acid disassociates. So we're going to subtract X over here. We're losing X amount of this because it's disassociating. But when we take apart HNO2, when we take apart X of that, we're going to produce X of H plus and NO2 minus because this has stoichiometric coefficients of 1 for each of these elements or species. So we have minus X, and then plus X and plus X. Our third step is to add down the columns to get equilibrium values. So we have 5.00 molar minus X. I'm just going to drop that molar because like we said, we know that only molarities go in here. And now we have 0 plus X, so we just have X, 0 plus X, we just have X again. So now we know what our equilibrium concentrations should be in terms of this X value. So what we're going to do next, our fourth step, is we're going to substitute our equilibrium values into our equilibrium equation. So our equilibrium equation is that Ka equals our concentrations of our products over concentrations of reactants. So Ka we know. We'll just write that symbolically real quick. So it's going to be our H plus concentration and our NO2 minus all over HNO2 concentration. So when we substitute, we're going to have 4.00 times 10 to the negative 4 equals X times X divided by 5 minus X. And this looks kind of complicated because there are a lot of X's here. But if you look at it, really you can use the quadratic equation to solve it. It's just that simple. So we're going to use quadratic to solve for X. And if you use that quadratic, you'll get X is equal to 4.5 times 10 to the negative 2. A simplification that you often make in this type of problem is that this bottom X, the X that's subtracted from the 5, so this one I'm circling here, is just ignored. So they would just have 5 in our denominator, which makes this a little simpler and you don't have to use quadratic. But that's not always a good assumption to make, depending on how large X is. So it's just as easy, I think, to leave it in there and use quadratic. So now that we know what X is, we can just go back to our equilibrium equation we have, or not our equation, but our values we have from our table, and we know that our concentration of HNO2 is just 5 minus X, which equals 4.955 molar. the concentration of H plus is equal to X, so that just equals 4.5 times 10 to the negative 2. And our concentration of NO2 minus is also 4.5 times 10 to the negative 2. So this is a icebox problem or ice table problem, and it's one of the easier ways, I think, to solve this sort of thing.